All right, let's get going, why don't we? Okay. So, we have some bugs in our computer. Whether they're in the hardware or the software, I am not yet sure, but I'm pretty sure at least some of them are hardware related. Let's take a quick look at what we have here. This is supposed to be dividing. And I think most of our bugs... Okay, let's see what do we have here. I can remember what the different parts do. Here. In my text editor. Okay, there we go. So this is group group 5, which is add, subtract, and compare. Okay. Yeah, add circuitry, subtract and compare circuitry. Okay. I'm going to move these apart a little bit so that they can be more apparent who belongs to who, and that they are indeed separate. Okay. Subtract and compare are supposed to be identical. The difference is that compare has the carry bit fixed on at all times. Basically, compare is subtract without carry and store to nowhere. Whereas subtract is subtract with carry. Store to wherever you want. Or store to A, actually. So... Let's see, I should have commented this a little bit better. We have our initiate block right here, which is pretty simple. We're just setting up the initial register state, doing our basic I/O, loading them into our initial registers, and then we do our initial subtraction. Oh, okay, yeah, we're comparing A to R0. Yeah. R0 is appropriately enough, in this case, our 0 value. It holds 0. And jump if not carry. I'm not sure if that's right. Yes, it should be. As we set carry here, we do subtraction. That part doesn't matter. Actually, does it matter? We don't need to clear the carry in here, because compare acts like carry was set. It'll be set or unset after compare, depending on the value of compare. Anyway, we jump if we don't have the carry set, which means that the value went below 0. And then we, otherwise, we do some value changing and fiddling here. And this is where we do our output. Okay. Problem is, I'm pretty sure this works with the 10 divided by 3, if I remember correctly. It falls apart. No, it doesn't work for 10 divided by 3. Why not? Oh, it's 2918. Okay, yeah. Let's go. Now it's doing 10 divided by 3. Yeah, I should have stopped a while ago. Okay, so what's the problem here? Step through the program. We do the initial load stuff. We don't care about that. We load R1 into A. This is R1, this is R2, this is A. We set the carry flag, which if we look at the flags, yes, carry flag is set. We subtract R2, compare R0, jump if not carry, carry is set though. Store R1, we load A into I. Or we load I into A, I mean. Which, that's fine, I should be 0. Set the carry flag to 0, which indeed does. We add K to I. Because we're storing 1 in K. Just because that seemed appropriate. I really need an add immediate instruction, which would be easy enough to add. Okay. Then we store A back to I. We jump back to the beginning. We load R1 into A, which is now 7 because we subtracted 3 from it earlier. Set the carry flag. Subtract. You always have to set carry before you subtract, because it just makes sense that way. We compare. Carry's still set. Jump if not carry, okay. Boom, okay. Now, at this point, R1 is 1. So when we subtract R2, we get -2. Hello, survey. And notably, it clears the carry. Okay. That is exactly what we want. Wonder if the compare is backwards. And do we really even need the compare? Let me try commenting that out. What's the comment character in here? There we go. Okay, that one came out correct. This one's gonna take a little while. Or a lot of while, as the case may be. It should work now that we're using carry, though. But it's at 30 right now. We need to wait for it to count up to 255. Actually, you know what? Okay, screw this. Let's stop it. Let's run it at 10 kilo. Okay, it's working. I think if I reversed this carry, this compare, and we compared the other way around, it would work. Or if we used a different jump condition, maybe. Okay, but anyway. That unlocked divide circuitry. You fools! You absolute fools! You gave me divide circuitry when I implement a software divide. Ha 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 ha, suckers. Okay, anyway, moving on. I think it is kind of funny though that I implemented a software divide and I got a divide chip out of it. I'm going to assume that my score is probably terrible compared to what you could do. Okay, so the next one is functions. Sometimes it's useful to reuse a section of code. We call these sections functions. To implement this reuse, one can jump from the beginning of the function, jump back again at the end of the function. We call jumping function, calling the function, jumping back, returning. Okay. This is why we have stacks. And this is actually why we have 2 stacks. Part of the reason why. You don't need 2 stacks for functions. Quite the opposite. But anyway. In this level, you'll be tasked with implementing function calls and returns with the call and return instructions. Okay. There's no tests. There's just a level is complete button here. Okay, we are not going to necessarily add call and return precisely that way. I mean, we will, but first of all, where'd OBS go? Okay, here we go. Boom. It's time for the text editor. Call and return. I'm going to implement these in group 4A. Because we have lots of space there, and this is related to jumping. So, sure, we'll just call them that. Call. And return. Those are good old traditional names. So they want us to implement call so that it jumps and then pushes to the stack. We're going to do some additional steps that they don't do. Because we have a slightly more complicated design than they have. So we have more things to worry about. So our call instruction is going to jump to the parameter. It is going to push the current PC, before it jumps, it's going to push the current PC onto the R stack, not the D stack, the R stack. It is going to also set the frame register to the current pointer, the current stack pointer on the D stack. So it's going to copy the D stack frame pointer to the frame pointer. And I think that should be enough. No, we need to push the frame pointer as well. I think we're going to push the frame pointer onto the R stack as well. I think we need to push the frame pointer. We'll do it anyway. So, we will push PC to R. Push PC to R stack. Some of this might be more complicated than I want to do, though, is the problem. Because we're going to be setting multiple things. It might take more than one clock cycle, which is going to be interesting. I might actually do a pair of instructions that we use together. I have to think about it. Because they can only do one memory access per cycle. So we're trying to push 2 values to the stack, we're going to have 2 cycles. We might not preserve the existing frame register and somehow restore that. Or we might just not use the frame register. We might not actually automate the frame register at all, on second thought. If you don't need the frame register, you don't need to do anything with it. Might be a good idea. Yeah, you know what? If you don't automate the frame register, all that means is that you're going to want to put your own instructions for restoring and pushing the frame register if you need to use the frame register, which is not the end of the world by any means. I'll think about it. I might include 2 different returns. Return with frame and return without frame or something like that. We'll think about it. For now we're doing push PC to RStack, because that's the only memory access we're allowed to do in this instruction. Because any more than that, and we're going to have 2 cycles, and this computer is not designed around allowing more than 1 cycle per instruction. We would have to do something fancy. Actually, let me look at this real quick. We are using dual RAM. Initially, okay, it's dual load RAM. We can't do dual stores. Okay, that's what I wanted to know. We can't do a dual store, which means we can't do what I'd like to do with that. We push PC to the RStack. Jump to argument. I think I'm going to have the argument be immediate. Yeah, that makes sense. Jump to immediate argument. And is there anything else important I need to do? I would like to preserve the frame pointer. There's a different way to do this too that doesn't use a stack, and that is to have a return register. And then what you do is the call instruction puts the return address in the return register. And it is the job of the program to handle saving that register. The same kind of way I'm thinking about handling the frame now that I think about it. We're not doing that because I don't have a register set up for that, and we have stacks sitting there handy, ready to go. But it's a way to avoid using processor managed stacks, which has security upsides. Because if you don't have processor managed stacks, then you don't need to worry about switching. You don't need to worry about context switching stacks that way necessarily. There's a bunch of reasons why it makes sense. For a simple computer like this, it makes no difference. But it's interesting to note that there is a different way to handle it. I don't think... Now that I say it, I don't think I actually need to do anything more complicated than this, because frame pointer handling... Yeah, you can just push the frame pointer to a stack, however you like. I would like to have the frame pointer more automated though, but we can't do it without making call to cycle. Unless we could add a second instruction whose purpose is to store the frame pointer, and then have return automatically pop the frame pointer. That sounds dumb. And it is kind of dumb. But we would end up with 3 instructions used to work with. That's not a particularly good name. I'll think of a better one. Okay, this. Push. Oh, wait. Wait. We can't do that. We can do another step in here. Okay. No, that's not going to work. I was thinking about having an instruction, have a call instruction that jumps to the function, have a function that is the first, or have an instruction that is supposed to be the first instruction in a function that saves the frame pointer. Wait, no, that'll work. What were we thinking? Yeah, that'll work. We'll just call this fuck. Actually, no, we can't do that. Because we would need to have another instruction yet. Because return, then you'd have the problem of return not being able to do cycle memory stuff. Yeah, okay, we're gonna have to stick with this. And technically you don't need return at all. You could just do pop R PC and that would work. And call, you can just do push PC, push R PC, then JMP and whatever. But we'll use call as a slightly cleaner way to do this. I don't think we're going to do return at all. We're just going to do pop R. If I did do return, it would probably be an alias for pop R. I'm going to add a note here though. Okay. Just move that off to the side. I already hid the thing for you. Go into the ISA and let's add the call instruction. This is going to be group 4A, which is right there. Okay, JMP is the only one we have in group 4A. Go ahead and add call. I don't know if I ever actually use that instruction. I probably will. Push PC to R stack. So we're going to want PC. Let's see. PC is instruction 4. Actually, this is the wrong place to implement this. Yeah, this is absolutely the wrong place to implement this. Boom. Let me think. Because we're gonna have to implement a bunch of, we're gonna have to re-implement a bunch of logic around push and pop if we do that in there. Let's see, push, pop, that kind of stuff is in group 2. Boom, group 2A. Okay, the problem is we have no room in here. Okay, how's push R implemented? Yeah. I would actually implement call and return on this as a macro, if that was a possibility. Due to the way our architecture is designed. We don't have any free space. Well, we don't really need any free space either. Because call is literally no. Yeah, call could be implemented very easily. We definitely do not have any room in here. This would be the place to implement it, though. Go back and look at our computer. If we did implement it... Okay, where's the push and pop engine? Here we go. This part we don't necessarily care about. We would have to re-implement at least part of this push and pop engine. Elsewhere, if you wanted to do that. No. Okay, functions are complete according to me. We just use 2 instructions for a call. Okay, there are 12 cards in the table between each player. Take turns with pick between 1 and 3 cards. Reading input will give you the current number of cards. Sending 1, 2, or 3 will number of cards. Okay. I do not remember the strategy for this particular little stupid game or what it's even called. Okay. If I remember correctly, this should be a pretty simple table lookup, basically. Because Whoever goes first can always force the other player to pick up the last card. Let's see if we can figure it out. Okay, so there's definitely a strategy we want to use for this, but I don't remember what it is. Okay. We take one. You took 3 and forces. Okay, yeah. Let's restart. So what we want to do okay. At this point we've lost, I think. Doesn't matter what we take, he can take less and force us to lose. Yeah. So we need to make sure it comes out to being 5 cards on our turn. We'll take 1. We'll take 2. Okay. Now we take 1. And no matter how many he takes, or wait, no, he's gonna take 3 and we lose again. Okay, yeah. What is the strategy for this stupid game again? I wish I remember what it was called. Oh, this is useful. Oh, that's not useful. All right, here we go. Okay. Yeah, I really don't care about your fancy mathematical proof. That is a completely worthless one, honestly. Yeah, this is all about figuring out mathematic probabilities. I don't give a shit about that. Useful either. Okay. And clearly, if we are forced to go first, there is a strategy where we will always win. I just need to figure out what it is. And the problem is I'm not sure. Let's just say we do that. Now he can take 2 and he can force us to lose. But he doesn't. Now how many do we take at this point? If we take 3, he takes 1 and we lose. If we take 2, he takes 2, we lose. If we take 1, he takes 3, we lose. So at this point, we're basically screwed. Yeah. Let's try this. Okay, we're right back at the point where he can force us to lose again. Okay, let's try some different combinations. If we take 1, and then take 1, we're right back at the point where you can force a loss no matter what. If we take 2, and then take 2, we're right back at the point where you can force a loss no matter what. Where are we? Yes, we are. Because if we take 1, he takes 3, we lose. No. If we take 2 and then 1, then we're right back at the good old point of... Oh, no, wait, no. Here we go. We win. No? What? Oh, I read it wrong. We take 2. Take 1. We take 3, he takes 1, we lose. Yeah. At this point, we've lost no matter what. What happens if we take 3 to start with? And we take 3 again. He can take 2 and we lose. We take 1. Then we take 3, he takes 1, we lose. Okay. We take 3, he takes 2. We take 1. We take 3, he loses. Okay. Okay. We want to work it out in such a way that there's always 5 cards left. And to do that, I'm willing to bet that they are going to vary the number of cards for different tests. So for this test, the solution is take 3 and then take X. Okay, let's say we take 2. He takes 1. We would have to take 4 at this point to win. So if we take 1, he gets us down to 5, at which point we've lost. So what we need to do is we need to take a number of cards. Wait, how does it specify the puzzle exactly? Does it specify how many cards he starts with? "12 cards, okay. Wait a second. If it's always 12 cards, then we can just hardcode this. Okay. Or, you know, hard code the basic strategy. Okay. Want LDI. 3. And then we want yeah, what instruction I'm looking for? S something. STA. Okay, there we go. IO. Is LDI the right instruction? LDA. Sure. No, it is LDI. Why did I call it LDI? Load immediate. Okay. Yeah, makes sense. Okay, we store that to IO. Then we do LDA, IO. Immediately grab the result back. This is probably where he's gonna vary how many cards he takes, isn't it? So then we just do a comparison and a jump. So if we take 3 cards, if he takes 1 card, here, let's take 3 cards. He took 2 cards. We need to take 1 card. We need to take 2 cards. Because there are 7 cards left. And we want to get it down to 5. We take 2. He took 1. We take 3. Boom, we win. Okay. So at this point, LA should contain the number of remaining cards. We want to get that result to 5. So we do... we need to load some stuff into registers first. Okay. We store A to register 0 for now. And then we... LDI. 5. And then we subtract. Actually, don't do that yet. R1. LDA. R0. We subtract R1. And the result, we write to the IO. Okay. And now we want the result to be 1. So we do this whole mess again. Except this time, instead of wanting to go to 5, we want to go to 1. Okay, let's step through it. This may or may not be correct. Boom, we take 3. Boom. Okay. Yep, okay. That wasn't too big of a deal. It was a little bit annoying, but it wasn't too big of a deal. That one we could have done quite a ways back, right at the very beginning of the leg computer. Okay. First, read 15 deliciousness scores from the input one by one. Task is to output them in sorted order, smallest to largest. It's going to be slightly annoying because I am a proper modern programmer. I don't write my own sorts, damn it. So we're going to implement a very bad sorting algorithm. Okay, so first of all, we want to just go ahead and load all this stuff in memory. Yeah, there's 15 of them. We don't have enough registers even if we wanted to. So we'll do it in memory. LDAIO. STM. Actually, do this a little differently. We want to go ahead and store our index value into I, probably. So let's do LDI 0. They want to do STA I. Okay. And we're going to have to do the next part 15 times, so let's do a loop. Okay. So we do LDAIO, STA, wait, STM, store to memory. We'll just use I directly. Don't need to mess around with offsets or anything. Otherwise, we'd use like LDMI or LDMK. STMI, I mean. Yeah. We could do STMI 0. Matter of fact, that might be a good idea. Because we might want more than one array. We can shuffle back and forth between them or something. But anyway, let's do it this way for now. And then we want to do LDAI. We need a 1 from somewhere. I really need an add immediate. Also, I would be helpful to have increment instructions or increment and decrement instructions for I and K. Let's go ahead and make an instruction wish list. I'm going to do that right now. Things I should add at some point. And okay. That'll be a problem for future Milo. We'll see if I ever actually get around to it. Got lots of room in group 5. In fact, you have just enough room in group 5 that we can add 4 instructions for adding and subtracting a fixed value from I and K. And 1 immediate operand add instruction, which we actually wouldn't need if we had the increment and decrement from I instruction. Also, why is spell check not working here? Okay, let's delete that. And let's bring up the good old text editor of Doom. We're down to group 5. And let's add some more instructions. Let's just do add and sub. Okay. So this will add or subtract a constant value from I and K. Yeah. Technically, we could do without a subtract I and subtract K. By using some negative numbers and fun stuff like that, but I don't think that's worth doing, no. We'll just do it the normal way. Additionally, I would like to have add I and sub I as add immediate and subtract immediate. And then use something else for this. If we do add and subtract immediate, the whole point of an I and K register is that they are specific registers designed for indexing that have special indexing operations attached to them. Namely, direct addition and subtraction. Right now we have room for 1 more instruction. If I just do add and sub I. Which are just add and sub, but with immediate operand instead of parameter from register. Then we have 3 more instructions. Implement. Okay. Increment and decrement will take a register as an argument, and it will add or subtract 1 to that register. That means that I won't have any specific, I and K registers won't have any specific meaning. Hardware-wise, well, that's not true. They will, because there are these load memory instructions that deal with them directly, I guess. And we would still have a third instruction left. 3. These right here will immediately make a lot of things easier, because it'll be A to immediate parameter to A. Okay, let's just do this. This will be easier. If we had a couple more instructions of budget. Okay, OBS. I used to have hotkeys for hiding and showing Sublime Text, but they became a problem, so I disabled them. Now I kind of wish I had them back. This is group 5? Yeah, group 5. I could add a group 5B and put them in there, but no. Add I. Subtract I. And then increment register and decrement register. Now, technically, we don't actually need to make these instructions at all. We can just make them aliases for add and subtract. With minor encoding differences. And that would work just fine. And we wouldn't need to make any other hardware changes to the computer. But I'm not going to do that. For a variety of reasons. Most of which don't actually make much sense, but anyway. So we do 0 here. 0 there. And we hook both of these to the outputs. Those need to be ons. Okay. And then these need to be 0. And these are left blank. Okay. There we go. Add immediate, subtract immediate. They're exactly the same as add and subtract, just with immediate operand. Increment. We actually specify the destination for increment. And our first parameter is the same as for the destination. Decrement is going to need some special logic to automatically set the carry. We already have a solution for that. We just need to tie it in. Okay. And then the second parameter is a constant value of 1. We could leave it -1 for decrement, but no, that's a bad idea. So actually, we could not implement this as a alias for subtract unless we required the user to set the carry first, which isn't necessarily a reasonable thing to do, I don't think. I think these are the only instructions I've ever done where we're passing the same register in 2 places. But there's no reason why it won't work, so. Alright. Constant, that's left blank. Constant, left blank. Okay, good deal. I do believe we're done here. Now, we need to go to the adder and subtractor, which are right here. And this one... Okay. That one goes nowhere as of yet. All of these go nowhere as of yet. Okay, so this is add I. It is exactly the same as add, which is this one right here. I think what we need to do here is just bring it in like that. And then we just do a little bit of diode action. Boom. We could use an OR gate there, but diodes are more compact. You know what? No. Let's use an OR gate. Do it the right way, not act like a bunch of barbarians. Okay. Now, this is subtract I. And for this, we can just bring it in exactly the same way as the current subtract is handled, but put a 3-bit OR there. And I'm probably going to regret this in a moment when it comes time to implement the de-increment. But that'll be a future Milo problem. And screw that guy. Okay. Move all this stuff over one more wire so we can... Now, increment. Remember what I was just saying about 3-bit ORs? And de-increment. Remember what I was just saying about 3-bit ORs? Problem is that de-increment is a little bit more complicated. We don't want to run it in quite the same way because it has to power this multiplexer as well, because it's a subtract without carry, whereas the normal subtract is subtract with carry. So, to that end, what we really should be doing is ORing these 2 wires together before this point. So these should get ORed. I'm not sure how we're going to do that because we're kind of short on space. What we need to do is make more space then. Okay. There. Now, we need another 2-input OR. Which will run to there. And then you go to there. You go to there. Not the most elegant approach in the world, but it should work. Yeah. Okay. Go ahead and clean those corners up a little tiny bit. Do this. I like the look of that slightly better. I can't drag that back any farther without making this wider. Could drag this up one though. No, I can't do that. It has to go back farther if I want to move it up at all. Alright, good enough for who it's for. A little bit annoying how I interlaced those, but it makes logical sense otherwise. Okay, back to our code. I'm just going to assume those work for now. So now we just do ink I. I need to add those as encoded things. Okay, where's add? There's add. Okay, so add is instruction number 1. Sub is number 2. Add I. Do the next one. This would be sub I. Ink. And deck. Okay. And then we just do jump. Load. Except we don't actually want to do that. We also want to do... No, we want to do... pair... You know what? I'm missing an instruction. I want compare media as well. Where should I slot that in? It should probably go before add I. Okay. How do I do these things to myself? Yeah, compare media is going to be incredibly helpful. I need that. Now I have to rewire this shit. I do these things to myself. Okay. Move this out farther. It's not like we're limited on horizontal space or anything. There. Okay, now this is de-increment, this is increment. This is here, let's just start from the top. Compare. This is going to need to be a 3-bit OR. Okay. Compare, add, sub, compare I. Draw out these a little differently. Okay, here. Compare, add, sub, add immediate. Compare immediate. Oops. Compare, add, sub, compare immediate. Add immediate. Subtract immediate. Increment. And decrement. Okay, so compare immediate, and decrement all run into the add without carry, or subtract without carry gate. And then subtract and subtract immediate run into this one directly. Alright, very simple. Now I need to go actually move stuff around in the ISA, which is always slightly annoying. These are group 5. Group 5. Okay, what needs to be moved? Increment, decrement, add sub I. Okay, so the last 4 instructions all need to be moved. It's annoying as hell. Okay. Hook that up. Add I is the same as sub I. As far as some of the wiring goes. Okay. And this gets changed to be CMPI. This compares A to an immediate operand and sets the flags, which means this needs to be set to -1. And this is indeed in basically, it should be encoded exactly the same as this, except this off needs to be a non. Okay, so that wasn't that big of a deal. Yeah, go away. Now, hello, Colo. Welcome here. Now we need to re-encode these instructions. Okay, where is increment? Decrement, okay. So we want sub as the last defined instruction in the previous group. And then we want to do this as CMPI. This is add I. Come on, there we go. That's sub I. This is increment. This is the increment. Okay. Still playing that game hurting game? It's not that bad. Come on. You want CMPI. We need to load LDA. Okay, let's see, what are we trying to do here? We want to load I into A. We want to compare I. And then we want to do jump if not 0. In other words, if they're not equal to load. So this should load these first values. Okay, let's test this part. This should run 15 times. Oops. Should run 15 times and load 15 values into memory. Okay, there's 16 in a row, so we're good. Short circuit on STMI. Why is STMI giving me a short circuit warning? Address is being... Why is the push circuit energizing? Oh, it's a MUX there. That needs to be... It needs to have a switch after the MUX. Okay. I see. Can we fit a switch in? No. Can we force it to fit a switch in? Not really. Not without moving a bunch of stuff around. Am I okay with moving a bunch of stuff around? Kinda. Okay. I think this will work now. If not, we can probably move everything down one more tile. Okay, and the same thing we used to switch the MUX? No. What value do I use for this? This one, I think. Yeah. Okay, that should work. We don't have any other cases where a MUX runs directly on the line, do we? Doesn't look like it. Why do we have a bare switch out here for? Okay. It's doing nothing, that's apparent. Okay, we're loading into memory appropriately. This should be the last time through. Right here. And we're done. Okay. So that part works. Which is good because we have several new instructions implemented there. Now, what do we need to do next? This is probably a bad time to admit that I have never actually written a sorting algorithm before. It was never something I needed to do. It was never something I felt compelled to do either, because there are two kinds of programmer in the world. There are fools who implemented their own sorting, and there are people who used well-defined standard library sorting. Well, okay, there's a third kind of person in the world. There's the kind of person who needs something very specific and knows exactly what kind of weirdo sorting system that they need for that very specific thing. But generally, if you're implementing sorting, you're doing something wrong. Good night, Colo. It's like writing time code. If you're writing code to deal with times and dates, basic time and date calculations, you are doing something wrong and you shouldn't be doing that. Knock it off. Go get a library, because time and date is incredibly complicated and there's so many different ways to do it wrong. Sorting is a high efficiency thing, and there are a lot of very dumb ways to do it, and there are a lot of very smart ways to do it. And usually, like I know for sure that the sorting functions in Go, it'll actually choose between multiple different ones depending on what it thinks to be the most efficient, based on the size of what you're passing in and a few things like that. But anyway, so let's just go ahead and implement something really, really dumb and basic. Basically, what we're going to do is we're going to walk through our array, and we're going to swap adjacent values until we can't anymore. And every time we get to the end, we'll set a flag. If we do the swap, we'll set a flag. And then every time we get to the end, we'll check the flag, and if the flag is not set, then we'll go back to the beginning and do it again. And again, until no more swaps happen, and then we're done. There's a name for that. I don't remember what it's called off the top of my head. Is that bubble sort or is it quick sort? I don't think it's quick sort. I think it's bubble sort. Yeah, bubble sort. So we'll do that. To be perfectly clear, this is horribly inefficient. It is the dumbest and simplest possible way to do a sort. And I am not proud of the fact that my first ever handwritten sort is going to be me fumbling around trying to implement a bubble sort. Okay. What register should we use as our flag? Let's just use R5 as our flag. So we want to do CMPI. Right here. LDA, R5, CMPI. Oh yeah, we could use the stack for some of this stuff too. Just do saves and restores and stuff, but then I had to set the stack banks, and I don't feel like it. Okay, anyway, CMPI. Compare R5 to 0. And then we... Actually, wait, we don't even need to do a compare. We can just load R5 into A, and then jump if not 0. Back to sort. Because loading R5 into A will automatically check to see if it's 0. Huzzah for the 0 flag, I guess. Okay, do we need to output anything at the end of this? I assume we do. Yeah. Output them in sorted order, okay. Then once we're done, we do... LDI, I, wait, LDI 0, STA, I, and then we do basically a copy of our load loop. We'll call it the unload loop. And we just do slightly different order here. We load from memory, which is LDM. Yeah, we'll do LDMI though. LDMI 0. Basically, we're saying load address 0 through the I register. Indirect to the I register. In other words, add 0 to I. We could do exactly the same thing, but just doing LDMI. Okay, so we loaded that, and then we just do STA.io. Then we do increment I, LDA, compare I to 15. We could actually improve this considerably if we loaded 15 first. Did it backwards. But we're not doing that because that would make the order in memory a little bit awkward. Not really, actually. I don't really care what order the array is stored in. We could store high to low, no problem. As long as we output in that order, and as long as we do the sort in that order. But you know what, let's do that. It'll make it a little bit easier. We'll do 15. We'll de-increment I. And we'll compare to 0, except we can do it. We don't have to do that. We just have to load I into A, and then we do jump if 0. Because we don't need to do the compare anymore. Okay. We don't even have to technically load it into A. We could move I to anywhere. And A is the only place we can really do it, but we could do anything that worked with I somehow. that would also set the 0 flag based on the value of I. I think increment I would be good enough. Because that should set the 0 flag afterwards. Or we need to do de-increment here. Yeah, this should set the 0 flag if de-incrementing I results in 0. We can remove a whole nother instruction for that. Okay. That'll make the load non-load loops a lot faster. Not that it matters, but that's the kind of weirdo stuff you can do here. Yeah, we're still going to need this at the end of the sort, though. Now we just need to implement a bubble sort in here. I should double check that this is going to run properly first. Why did it write that to location? Oh, okay. I think this needs to be 14. Well, let's... Wait. What'd you do? Oh, jump if not 0. No? Wait. What happened here? Okay. LDAIO. STMI. De-increment I. Which worked. I is now 14. Did it not set the flags correctly? Negative is set. Why in the hell is the negative flag set? We better go look at what de-increment is doing. Okay, first of all, let's start at the registers. This is energizing the I register for both load and store. That's exactly what we want. It's loading 15, it's storing 14. It's exactly what we want. And then we go down and look at the math. Okay. We're doing a subtract without carry. Oh. Okay. I'm not sure why negative is set here. Doesn't make a whole lot of sense, but it is setting carry, which is technically correct. And 0 flag. Okay, that's all correct. This is jump if 0. Need to jump if not 0. Okay, that is correct. Let's start over. Okay, now it's working. And I think this is going to go one past the end because I screwed it up a little bit. It needs to be 14 instead of 15. Try this properly. Okay, no, because it does need to be 15, and we need to move the de-increment to the top if we want this to work that way. Which would mean extra instructions, so no, we're not doing that. we will STMI 1 isn't right. I could say -1 here. That would definitely be wrong because it's not going to work that way. Actually, if we put 255 in here, that should flip all the values. Let's just try it for the dawn of it. I think actually we need 254. I think. No. 255. That's not right either. It's close. Yeah, that doesn't work. We just do 1. What's that? It's definitely not going to work. Oh, I know how to do it. We set the carry. I forgot that step. No? Okay, well, it's not worth messing around with. We'll just go ahead and have it offset by 1. It just looks different in the memory, that's all. Wait, now it's doing what it's supposed to do from the start. It's not going to load the last value though, is it? We need to have it set to 15. Yeah. Derp. Oh, that's why it wasn't working. There we go. This isn't going to work even. Actually, no, it did work perfectly fine. Okay. Yeah, we can do STMI 255 with 15, which is technically 1 too large, but and it'll just result in stuff being laid out from 0 to 15 indexes. Technically, we should do 14 and set the carry flag, but no. Also, why am I doing this? Because I'm an idiot, that's why. We could also just do it from 1 to 16 in memory and be happy. I think. If you set this set to 15. Let's try something. 0. I want to see if this reads 1 time too many. I think it actually will. No, no. Spam clicked past the dumbass. Yeah, no. That's correct. We're wasting that first memory slot. I'd really rather do the check at the top instead of the bottom, but it's more efficient to do it at the bottom. Hello, Treebeard. Yeah, let's just do this because I think it's funny. And it's something that we can do. All right, now bubble sort. To do this, we're going to want to go one at a time. So we'll start out by loading zero into I. And then at the end, we will increment I. Okay. Kind of want to do no. I want to increment I at the beginning. And I want to load 0 into I. And I want to load -1 into K. Because we're going to use K as well. So we do LDI 255, STA, K. And then we do increment I, increment K. And then we do our check here for whether we're done sorting. And then we do our check to see if we're done with the loop. Which actually... Are we doing this wrong? Because we're counting backwards again. I keep forgetting. We want to do the increments at the end because that'll save us jump not 0, sort. And then we want to do the increment K, the increment I. And we want to load K with, we want to load I with 15 and K with 16. Except we don't want to. We want to load I with 14 and K with 15. Because we're not going to go through the whole array through all 14. We're not going to go through the array 15 steps. We're going to go through it 14 steps. Because one of the members, we're always comparing two members. But one of the members had to be compared to null if we went through all 15. We're not doing that. Because that'd be wrong. Now, actually, this goes at the end. And we don't go back to sort. We go back to here. Yeah, we do go back to sort. We will call this bubble. Bubble is the inner loop, sort is the outer loop. Okay. Go ahead and do proper programmer things and indent it. Okay. Fully through that. So what we want to do here is we want to load I, want to load K, we want to compare the two, where I and K are places in memory. We want to load those two values, we want to compare them. If one is greater than the other, the wrong way around, we want to swap them and write them back out, otherwise we just continue. So let's do LDMI. $255. And then we do C. Am I doing this backwards or the right way? Guess we'll find out if we end up sorting things reversed. We will store this to R0, so we do STA R0. And then we do LDMK. $255. Because we're doing weird things. Probably shouldn't have done any of this, but oh well. Then we do CMP R0. This compares A to 0. Now, if the value is less than, we will get the negative flag. Here, let's just run it and see what the flags look like. So here, let's set a breakpoint. I don't have to spam click. Okay. We load 216. We store that to R0. We load 251. We compare the two. And the result we get is negative and carry. Go down here and look at the ALU. Or in this case, just the AU. The L part is elsewhere. We have $251, $216. And I think we actually want to deal with the overflow flag. No, this makes sense. I should have wrote down exactly what the flag's meaning is when comparing. In this case, we want to do an unsigned comparison, which means I don't think overflow is meaningful. Negative would probably be the most meaningful thing here. Let's see. I need to document the compare instruction a little better. Carry should be, I think, greater than or equal. So we're looking for carry not being set, I think. In this case, these two are sorted in the right order, so we don't want to jump. And carry is appropriately, pretty sure, not set. Or not going to be set. I clicked out of this and screwed it up, of course. Wait, what's up with this mess? Okay. We want to go to there. Here. That's a terrible idea. Can't tell what it's doing if I hit the 10K button. Boom. Okay. So this will have the carry set. So we're looking for if the carry is cleared, I think. Yeah. I think. Okay. Jump if carry. Do next. And we just do label next. And in this section, we implement the actual swap functionality. Am I building a computer or a food truck point of sale system? I'm implementing a bubble sort. In other words, I'm sorting the numbers that are beneath this. The food part is meaningless. Okay, so swapping. We loaded I into R0 and K into A. So now what we want to do is do STMI, STMI. Where'd that damn text editor go? There we go. Yeah, STMI is the correct instruction. Parameters and immediate offsets, we do 255. And then we do LDA, R0, and STMK. Is this the right order? We load I, we put it in R0. We load K, we keep it in R0. We store that to I. We load R0. We push that to K. Okay, yeah, that should swap everything. Because we do I, K, then I, K. If we wanted to do things out in the same order, we would do I, K, K, I. which are there in the right order already. We don't need to do anything. We just go straight to next. Is there anything else we need to do? Yes, we need to set the flag that we did a flip. So we do anchor match R5. Oh. There. Technically, we're just checking to see if R5 is not 0. And if we did longer arrays, we could eventually overflow R5. Or if we do enough iterations, we could overflow R5. So we really should reset R5 at some point. We're going to want to reset R5 at the top of each sort iteration. So let's do LDI 0 STA R5. Okay. Now, I should be adding way more comments to this. Oh well. This should work. I am not going to give any kind of confidence whatsoever that it actually will. Well, let's just try it anyway. Moving stuff around. Okay, it is slowly bubbling the values up. Emphasis on slowly. This is going to take a long time to get done. Because each time through the loop, it can only move a value one space. This is why bubble sort is so terrible. Like this 199 right here in memory. That needs to go right here somewhere. Probably farther down, actually. But it's going to take it a while to get there because it has to slowly bubble down. That's why it's called the bubble sort. The smaller values bubble to the front. I think I'm sorting this backwards though. Because we are counting from high memory to low memory. So I'm going to have to reverse these conditional checks. So let's do that right now. Let's just do K, I, and then we do A, I. And that should reverse the meanings of the comparison. And it should hopefully work. Okay, so it's loading memory right now. Starting from high and going to low. And indeed, it is now pushing the small numbers to that side of the array instead of this side. All right, let's stop this and let's just hit the 10K button. Because I don't feel like waiting for it to sort who the hell knows how many arrays using incredibly slow methods. Okay, there we go. This isn't the right puzzle. I want to go back and look at that again. Yeah, here we go. Here is our sort. Why is this set to... This is why bubble sort survives it all, because it's so incredibly simple. This block is reading the input into memory. This block is outputting the result. So this little tiny block here in the middle is the entire sorting algorithm. And it's just a pair of loops. If I was to write this in a modern programming language, it'd be like a small handful of lines total. But it's so slow. All right. What is this one? Fruit tasting event in the canteen, huh? We don't want to make sure, but we wanted to make sure we don't get the same fruit twice, as it would obviously be embarrassing. Scan the conveyor belt for fruit incoming at regular intervals. As soon as you see the same kind of fruit twice, turn and press the control panel. Oh, this is a robot thing. Okay. Yeah, we'll have fruit coming in. Control panel here. We need to move the robot up to there. Scan the... Okay. Guess I'll have a pain in the butt. Okay, can we move through that sign? No. Okay. Yeah, we have to get there more quickly. Okay. So the fruit are going to be coming hopefully at completely regular intervals. Okay. Let's just go ahead and program the code to get him to go up to the conveyor belt. Okay. So we want to turn left twice. So we do LDI. So let's do some constants first. Const left 0. Const right 2. Const move 1. Const wait 3. Const I'll use is 4. We don't need to shoot here, so we don't need to encode that instruction. All right. Now we go LDI left STA IO STA IO. Wait, we only want to turn left once. Then we want to do LDI right. Program that might sleep and it'd be faster. You know what I would do for sorting I already gave this little speech, but I don't know if you were listening or not. I wouldn't. Because the amount of time and effort it would take me to write a sorting algorithm that would be faster than what is available in the standard library of whatever language I'm using would not be worth it. I would never do it. You don't write your own sorting algorithms. Not unless you have a very specific use case and you know exactly what you are doing. And you don't know exactly what you're doing and you do not have a specific enough use case. And as I said before, it's exactly like writing your own time and date handling code. Don't do it. Because there's so many nuances to time and date that you will, not if, you will shoot yourself in the foot. Don't do it. There's a lot of things like that where it's super complicated, there's so many edge cases, or it's some hyper optimized thing. You don't write your own. Now, sorting algorithms are taught a lot in college for like a intro to programming kind of thing, because they're good for teaching somebody things like complexity, bringing out time complexity of an algorithm, because it's a good intuitive way to demonstrate time complexity. But I did not learn to program in college. I learned to program by programming. So I never wrote a sort. That was actually, today is the first time I ever have written a sorting algorithm. Obviously, I knew how they worked because I was able to just sit down and implement bubble sort, but it was not something I had ever had a need to do. So there we go. Very first time I ever implemented a sort, it was doing it a terrible way that you should never ever be done. And I did it that way on purpose because I'm lazy. Go me. But anyway, moving on. Once we turn left, we want to move forward one step. I was trying to figure out here if I wanted to do this as a function call. I don't think I do because call is 2 instructions. No, it isn't. Because we just do push R left or whatever. Because we don't need to worry about saving any registers. Because these would be super simple functions. Yeah, you know what? Let's do that. Let's just change all these constants to labels. Let me just do this. LDI. STAIO. And then we do pop R, PC. This will necessarily clobber the A register. But there we go. We'll put these at the end of our code. Boom. Okay, that'll slightly reduce the length of our code, but it'll actually make it take longer to run. But anyway. This is an amazing example of why reducing your code size does not necessarily make your code faster. Less code is not faster code. Because we're going to implement an extra push and an extra pop for every single time we do a movement. I don't know if this is going to be a problem. I think we should have enough time in between. I guess we'll find out. If it is a problem, we can just revert it. Okay, left, move, left again. Oh, wait. Yeah, left, move, left again. He's facing down. So turning left will face him here. And then he'll move to there. And left again will face him there. And then we want to do... Like, see, this is the case where it'd be way more efficient not to do it this way. Not working. Oh, I'm a derp. It's not push R, you idiot. It's, You know what? I need to go implement call. I'm not sure what I was thinking. Yeah, it's a 2 instruction thing to call a function. Because we need to do push R, PC, then store a value to PC. It'd actually be a 3 instruction to do call constant. Let's go implement call. I should have just went ahead and... I didn't implement call because it was going to be a pain in the butt. Because we'd have to have a push engine for call. We don't need to do anything special for pop R because that's literally just popping off and putting it into C. Yeah, we're going to want call. It's worth it. Where am I going to stick it? In group 4A. Okay. The group 4A is jump. Okay. Yeah, let's go with my call. I should have done this a while ago. Well, first of all, we need to go set it up inside of group 4A. Actually, no, first of all, I'm going to go ahead and build the engine. So, the jump engine... Oh, where even is the code that handles jump? It's group 4A. Which is this. So this right here is the call instruction line. What am I even doing here? It's handling a multiplexer that is swapping between overflow flag. No, okay, this is setting the this is turning set overflow on and runs into the program counter or feeds this value through. We're either jumping to a hard-coded address or we are setting the overflow. Okay. Okay. So this is the address part of the engine. What parameters do we have left free? We have parameter 3 available free. We're gonna have to hard code a bunch of stuff in here. Here's the push engine. We're gonna need to energize some of these lines up here externally. Specifically, we're going to need to ask for loads. The way this works is completely opposed to the way I need it to work. Actually, no, because arg3 select is asking for what. Okay. So we're going to need to energize this line to ask for register. And then we're going to have to energize it. We're going to have to energize it by setting the right stack register on register 3. That's kind of a dumb way to handle it. And then we just implement a simplified version of the push engine. We are extremely lucky that this does not use register 3 and this does, in such a way that we can still implement this properly without having to do anything fancy. We'll just go ahead and put in a 3-bit OR. And run a line right on down. A bit janky, but it'll do. And then what we need to do is we grab a diode, put it right there. Boom. Okay. Grab another line out of here, for which we need another diode. There we go. Okay. So that is this part of this operation solved. We still need to do the actual push engine, but yeah, we need to send a value on memory V, which basically we need to bridge PC and memory V together. Okay. What's this? This sends on bank. Okay, that's what we need to do. We need to send on address. We need to send on memory V by bridging PC and memory V together. We need to energize memory store. Okay. Hello, Sealith. It is indeed a weekend Milo stream. I have a feeling we're getting to the end of this game, though. There's not many puzzles left. Alas. My sadness is large. Okay, so we need to implement group 4A. So, go. Boom. Okay, call is exactly the same as jump. Except oh, we don't use argument 1 either. Oh, that's because argument 1 is... Yeah, argument 1 is related to... I think we could actually use argument 1 here if we had to. Anyway, we need to use this argument. And we need to set it to the R stack pointer, which is RP, so 6. And that is a register. And then we need to set our destination to PC, so 4. And this should work. With a little bit of extra code that we need to add yet. Okay, now we need to add a push engine for this. And this push engine, we need to copy PC to... this is going to be annoying as hell. Okay, first of all, let's move some of this stuff down. We need to make room for more lines. Let's just make a bunch of space. We're not going to need this much space for sure, but we can compact it after we figured out how much space we actually need. Okay. So, we need PC, which conveniently is available on here somewhere, I think. Did I remove PC from this? I removed PC from the bus. Damn it. We can get PC back on the bus as argument 2. Yeah. Because our argument 2 is always hard-coded to be ignored up here. You think? No, argument 1 is always... Okay, anyway, whatever the point is, we can go into the component factory. We can go into ISA 4A. And whichever one of these is not being used, which is this one apparently. Parameter 1, we can encode to be PC, which is register 4. Okay. That gets us the PC register on the bus. Okay. Boom. And then we need to copy PC to memory V. Yes. We need to energize memory store. Oops. Okay. And these switches need to be moved up one. Boom, like that. We need to energize memory store. And then bank should already be provided. We need to provide address. Where are these guys getting address? They're calculating the address. Okay, we should be getting the address in on result or argument 3V, I think. Yeah, that makes sense. This is such a weird special case. You guys maybe should play this game. You'd like it. Why am I both reading and writing to arg3v? This goes to address, you dumbass. Okay, there we go. Bank. We're energizing the bank selector up here. We're supposed to be energizing the bank selector up here. Oh, there's diodes here to prevent this from just... Okay, we need to energize more than just that. We need to energize... Can I move this OR gate down one? Yes, I can. Okay. Boom. Put in a 3-bit OR. And then we'll just run an extra wire right up through here. Okay, that should energize it completely and turn on the right bank register. Good deal. Ah. And it is the R-stack bank register, which means we have that configured correctly. Yay! So, memory V, memory store, bank, and address are all energized. That should be correct for doing a push. Okay. So our push engine is almost done. Now, we are energizing RP, which means we need to provide a value on this line. And that value will be easy to calculate, question mark? Every time it beeps like that, I get really concerned. Because for those of you who don't know, that beeping noise, which I assume you can hear, because I don't think there's anything that would stop you from hearing it, is a script that I have running in the background that will helpfully alert me if anything is going horribly, terribly wrong with my internet. I shouldn't say horribly, terribly wrong. But basically, one beep means inability to ping, or that a ping has been dropped. I lost a packet when trying to ping Cloudflare, because Cloudflare is always there. 2 pings, or 2 beeps, means that it lost a ping to Cloudflare, but then immediately was able to ping it successfully thereafter. So you should be able to hear those. But if you ever hear a single beep, then something weird is going on, because Cloudflare has gone down, and you should probably be looking out the window for mushroom clouds. Let's see. Specifically Cloudflare DNS. So 1 dot. Usually I only run that script when I'm expecting internet trouble, or when I've been having recent internet trouble. Okay, so we need to add a constant. Actually, we don't need to add anything. This needs to be wired to argument 3, the value. arg3v is this bottom value right here. Okay, so this should be the RStack register. So this is basically my push engine. Or a very abbreviated version of the push engine. Now, we do still need to differentiate Stack Overflow from memory overflow. Okay, overflows. We could get a program overflow here, but I doubt we'd ever have that happen. Do we have a way to provide that externally? No, we don't. We need to run another wire. And this needs to be through a diode. Okay. We need another diode here. And that should allow us to set the overflow if we get a stack overflow here. I think it was that simple. We just pull the carry, feed it to the overflow line. Yep, okay. Because this little bit right here, these 3 gates, are the incrementer part of the push engine. This stuff over here is the actual push engine. A little less complicated than the de-incrementer part of the pop engine. But anyway. So that should be the call instruction. It should, emphasis on should, function. Let's go find out how bad they are broken. Okay. The problem is, and I should have foreseen this, we are pushing PC as the destination to return to. We need to return to PC plus 2. Oops. So, we need to push PC plus 2 instead of pushing PC. Which conveniently we have PC plus 2 available right here. Well, right here, actually. So we're getting PC in on this line? No, that's not right. It's argument 2. What are we using? We're using argument 1 for something. That's for the memory value, which should be PC. Yeah, that's because we were pulling in PC on argument 1. Let's go change that now that we no longer need PC, now that we're using the value out of the adder. Actually, we do still need PC to be brought in argument 1. We're just accessing it indirectly. Okay, so we don't need to change anything. Matter of fact, if we change anything, we break it. All right. Move left. Boom. Okay. So we turn left, we move over here, we turn left, we move, we move, we move, we move. Then we need to turn right. We need to move. We need to turn left. And we need to move. Okay, let's see if we can get through all this without the first fruit getting past us. We might actually be too slow. Wait. We need to move. Turn right. Turn left, you dumbass. Like you never properly learned left and right or something. Okay. Okay. I'm going to add another instruction here. Halt. Which just stops program execution. Takes no arguments. Well, it has to take an argument. So I guess it'll just halt with an error code or something. I don't know. Actually, yeah. Halt with the code. Where should we stick this? What group? I'm kind of tempted to stick it in group 4A, because then it'd be with jump and call, even though it's not technically a jump instruction. We have plenty of room in group 4A. Oh. Okay. And execution with an error code. Let's go implement this. There is... The reason I'm implementing this is because I specifically saw a component designed for this. So, ta-da, there we go. Unfortunately, I can't actually set the message programmatically. So, how's the 7-segment display work? Okay. We would have to put in a 7-segment decoder, and I don't feel like doing that. Is there an easy way to just display a value? I mean, kind of. Just run a wire. Alright, let's just put in an 8-bit register. This register's sole reason for being is to store the value of halt. And we'll go ahead and use argument 3 because it's conveniently available right here. Yeah. So we can stop by here and check to see what the value we provided to the halt instruction is. This is totally extra and unnecessary, but... Okay, group 4A, which is starting to turn into a bit of a weird everything I couldn't fit someplace else thing. Okay, or argument 3, which is this one. Has a constant parameter. That should be all we need to do. Let's see how well that works. Actually, wait here. All is the last implemented group 4 instruction. So we just go like that. Halt. Okay. Run the program. Hit halt instruction. Boom. And if we go down to look at the halt instruction, we can see that the code was 0. We'll change the code to 5 just to make sure this is going to work. Run it again. Actually here. Apparently I can't run it faster. Halt instruction, reason code 5. Alright. I'm tempted to run a wire from this up to the main computer control. So I can have then put in like a 7-segment decoder and all that fun stuff and have it actually display the reason codes. No. No, I'm not doing that. Slightly tempting, but no. Because realistically, we're not going to use halt much. Okay, so we get there in plenty of time. So we're not actually being limited by our movement speed here. Now we wait. Let's go ahead and put that in there. Here. At this point, we're going to have a loop. How am I going to decide if I have never seen a fruit before? Let's add another function. We'll call it press button. We'll just call it press, actually. Okay. So what we want to do here is we want to turn right, use turn left. And I'm not going to use the actual right and left instructions because I have a feeling that this is probably going to be a bad idea. As far as speed. Are we? There we go. Being weird about letting me add more lines. There we go. Okay. Turn right. Use. Turn left. Go. And return. Okay, now. If we see a fruit we have not seen yet. Or wait, no, it's if we see a fruit we've seen already, then we press the button. The problem is fruit moves forward one tile every single time we do anything. Actually, no. It's not every single time we do anything. It's every single time we issue an action. I think. We actually would be okay to call functions in here. Now let's try that. Call. Right. Call use. Call left. Okay. That should work. Yeah, because we can... Or can we? Does the world move every single time we issue an action, or does it call every single time that there's a computer tick? Let's just insert some dummy instructions. And check this. I don't think it does advance. Yeah, no, it moves in lockstep with the program. I'm 90% sure. Yep, okay. So we can have whatever kind of slow, bad array search we want to do. Okay. That's what we're going to do. We're just going to do a simple array search. Because I'm lazy and I don't want to spend a lot of time on this. So, we need to do an outer loop. Well, we need to do several here. We're going to have to do several waits to get the first fruit there. So let's find out how many waits we're going to need. And also I want to see what the belt is encoded as. Okay, 92. I think what we're going to do actually is I'm not going to assume the fruit are coming at a specific speed and hard code that because I don't have to. What we're going to do is we're going to loop this makes me wish I had decided to go on to phase 2 already at this point. But oh well, we're not doing that yet. Phase 2 is a secret. So we're going to want to loop. Which means I'm trying to decide which registers I want to use for what. We need a loop counter. We're also going to have counters that we use for... Okay, we're going to need a counter for the outer loop. I think we're just going to use I for that for now, and we'll see if we need to save I later. So what we'll do is we'll do LDA, or wait, LDI. We don't need a counter for this. This is an infinite loop. Label, Dan. Then we just do JMP, Dan. We'll leave the halt in here just to keep it so that if anything ever happens that we somehow fall through here, we don't start running the functions in order or something equally weird and end up overflowing the R stack and having all hell break loose. This is just kind of a safety guard to make sure we don't fall through into the functions, basically. But anyway. Could remove this, by the way. Actually, no, we don't want to move that. We want to move that. Okay, Dan. What was the conveyor belt? 92, I think it was. Okay. And we get what we see by reading. Yes, this ID number is also the computer's input. Okay. So we want to do LDA, IO, CMP, CMPI, do nothing. And then if jump 0, we go straight back up to no. Jump not 0. Let's put the weight at the top. So we wait, then we check what's in front of us. We compare it to nothing. If it is nothing, then we jump to scan. If it isn't nothing, then we need to check to see if it is in our known list. Okay. if we know about it. Then we do something. Okay, so in this case, we're going to do here. Let's store temporarily store the fruit ID in R0. And then we load 0 into I and K. Oh, I need to set the bank. What is the bank? Okay, where is the push and pop? There we go. SRMB. Set the R stack memory bank. We'll set that to 1. Okay. We've set the bank. Because we don't want the R stack interfering with our memory use in bank 0. Because I don't want it to set the bank register and that bullshit. And we already determined that the R stack is working properly for call purposes of call. Okay, now we load 0 into I, or A, I mean. Then we STAI, STAK. I needed I and K for something. What was I going to use them for? We're going to use the loop counter through this loop, which we'll be using to read our array of what we found so far. Oh, no, we don't want to zero out K. We want K to be pre-zeroed out, which actually, let's do that up here. LDI 0. Technically, we don't need to do this, but I'm doing it anyway. STAK. As in our computer, all the registers always start at 0, but we want to zero them out just in case. You never know. Finally finished Dragon Slayer 1. Now wear a rune plate body. Congratulations. You can wear the best of the crappy armor. I shouldn't say that because I think the best armor I have right now is a rune plate body. I haven't bothered to get anything better or even check out what options I have for better yet. I'd likely have to go do some kind of event type stuff to get better armor. Anyway. Better armor is a low priority for me. Let's put it that way. At least melee armor. Remember that quest many, many years ago? Join the dark side, Treebeard. Return to old school grind for capes. No, don't. Save your life. Anyway. I think my original account back eons ago when RuneScape 2 was all there was, and they were just talking about closing down RuneScape Classic. I think I completed all the quests except Dragon Slayer 1, which was just called Dragon Slayer back then, if I remember correctly. It was the top tier free-to-play quest. It was the only one, or like one of the only ones that I hadn't completed. That was a very long time ago. Dread, of course, predates us all, or at least predates me. I don't know about Treebeard. Oh. We clear out the I register. And then, actually, we don't want to clear out the I register. We want to set I to K. Because K is going to be the maximum value. And we're going to want to count down so that we can use the jump if zero trick. Okay. Help if I press the right button there. We don't really need a... we don't need a not found label. We just need to do jump scan right there and do jump. Jump if zero, scan. Otherwise, we want to jump back to the top of this loop. Okay. We don't need this label at all. Yes, we do. Yeah. But we need to jump here from farther up. In here. I think I would have started... I would have had to have started in either 7th or 8th grade, and I think it was probably 8th. So I probably would have been about 14. It almost has to be 8th grade. I didn't really get much time to play because I really didn't have access to the internet very much back then. There was only a brief window of time where I had access to the internet with any amount of time at all. But anyway. That was back when you could still load Java applets in web browsers. Okay, so in here we need to check if the value at I, so LDMK, oh, LDMI, I mean, 0, oh. No, we do need a not found thing. No, we can put it in here. So what we need to do is we need to have a thing in here. No, we don't. It's a terrible idea. Yeah, we do need to have... We do need to have a not found. Damn it. There we go. Okay. So what this needs to do is it needs to add it to the array. So we do increment k. Before we increment k though, we need to do stmk r0. Something like that. Yeah, I'm pretty sure I wouldn't be able to remember the password for my old account. And the email for it is long gone. So, rip, never getting that back. I definitely wasn't able to remember the password the last time I tried to reacquire it. There's no hope now. Plus, who knows if the account even exists anymore, yeah. Yep, probably got migrated to RuneScape 3. If I got retained at all. Okay, what am I doing here? Store memory decay, R0. Is this what I want? Store memory indirect K, parameters and immediate offset. Okay, this is not actually what I want at all. We want to do LDA R0, then STMK 0, and then we want to increment K, and then we want to go back up to scan. Okay, if we found it, on the other hand, we want to call, what do I call it? Press. Damn it. It's so easy for this little window here to lose keyboard focus. Okay. Let's run through this again mentally and make sure it's right. We increment I. If it hits 0, then we did not find what we're looking for, so we want to go down here and we want to store it at the end of the array, and we want to increase the size of the array. K is storing the size of the array. If we find it somewhere in here, we want to jump to found, whereupon we want to press the button, and then we want to go back up to scan, which starts the process over again. Otherwise, if we did not reach the end of the array, we want to jump to search, which continues the search array. Okay. And this part here needs to happen outside of this loop, because this is setting up the loop counter. We don't want to set up the loop counter every single iteration. That would be bad. We want to do LDMI, which loads a value. And then we want to do CMP to R0. And if they're equal, aka jump 0, we want to go to found. Except I'm going to do this a little differently. To move this code around. There's no reason for found to be at the end. Okay. And I'm going to change this up a little bit too. We don't need this not found thing. Wait. Okay. So we found it. We do our thing. Okay. Yeah, this needs to be this way. I think. Working on getting things in order to get mining guild levels. Just need your mining to get to 61 and upgrade to the dragon pick and mine so much iron. I just finished last night getting the last unidentified mineral I needed for the expert mining gloves. I'm like pretty close to level 94 now. That was so boring. Mining coal. I was mining coal with the normal mining gloves, which gets you a lot of coal and is supposedly the fastest or one of the fastest ways. Second fastest way to get plus you have to remember where the blast furnace is. You want me to tell you? Anyway, I mined so much coal last night. Finally got the stupid gloves. I've been mining coal for the last several days to get them stupid gloves. It was a massive pain in the butt. I think there's several quests you have to do actually to get access to where the blast furnace is, but oh well, you'll figure it out. You're a smart guy. Anyway, so I finally got them stupid gloves. And then I was, oh yeah, I can go back to Motherlode. So I went back to Motherlode and mined for a little bit, and it's like, why am I mining in Motherlode? I can do blast mine. So I spent the rest of the night gathering materials to make dynamite. I think I have enough to make like 500 dynamite. Except for the wool, which I'm just going to buy because I have better things to do than shear sheep. And the pots, which I'm also going to buy because I have better things to do than make pots. I still have like, it's going to be sometime tomorrow before I actually get a hold of the charcoal I need to make the dynamite though, because I still have to cook for a while. Like 16 hours cooking charcoal. Anyway. This is why we comment things, because This code is nigh on unreadable. Anyway, long story short, it hopefully will work. A should start equal to 0, which means if we set I to 0, which is what we do right here, we need to do a little quick check at the very top. I think we need to go straight to continue. No, we just need to do store A, and then we do jump 0, not found. Boom, right at the very beginning. Skip the whole loop and go straight to not found if it's the very first item we find. And that should set K to 1. And then we can do the loop the next time. Okay. I think that's right. We have 106 instructions already for this. Let's just run it and see how it blows up. Okay. Let's go look at our memory. Okay. It actually worked. Good deal. I'm surprised I only had one test for that. It didn't make it run a little longer. Because apparently it was good enough to identify the first. Alright. Let's see, the earliest we could have done that was before even unlocking the stack, we could have done that. That's kind of ridiculous. Okay. Now, let's do these two. Had an intern type out planet names in human script. Unfortunately, forgot to capitalize each name. The inputs in this level represent the characters in a list of planet names encoded as ASCII. Each name is separated by a space, which has numeric value 32. Of course. Replace the first letter in each word with its uppercase counterpart. The possible input characters are A to Z, lowercase, space, apostrophe, and dash. Okay. So we're scanning for spaces. This should be quite simple. We want to have a loop. The way ASCII works is there's an offset between lowercase and uppercase, and you just add. So what we want to do here is we want to do LDA-IO, then STA-IO. This will copy the input to the output forever. And I can't remember where the manual will tell us. Boom, ASCII. Okay, here we have a nice handy encoding chart. Code page 850. Oh, they even have the APL in here. Yeah, APL's insane. Let's not look at that. That'll hurt your brain. Good old code page 850. So, if I remember correctly, yeah, capital A is 65 and uppercase or 97 is lowercase a. So you want to check if the numbers are between 97 and where's Z? Boom, 122. Basically, we don't care about that. We just want to subtract the offset between the two. Which is... Actually, I think it's one... Now that I think about this... Where's that open calculator? If I remember correctly, there was some property of ASCII encoding that where it's like 1 bit different between upper and lowercase. So we want... What was it, 65? Okay. Let me write this out. So 96 is 0, 1, 1, 0, 0, 0, 0, 0. It was... No, it wasn't 96, it was 92. Wasn't it? Okay, 65 is A. Why was I thinking 96? It's 97, dumbass. Okay, here. Clear everything. 97. It's just 1 bit different, obviously. Okay. That's lowercase a. And uppercase A is 65. Which is 0, 1, 0, 0. 0, 0, 0, 0. Okay. I think I already know what the difference is here. And uppercase Z is 90. Which is 0, 1, 0, 1, 1, 0, 1, 0. And lowercase z is 122. Which is 0, 1, 1, 1, 1, 0, 1, 0. Okay. So, if we flip bit 6, I'm willing to bet that it will flip between upper and lowercase. So, we're going to have a flag. We'll use the I register for this. Let's just do CMP I 32. And then jump 0. Wait, no. Jump not 0 to continue. Yeah. Boom. And then here we do increment I. Now, we need to do the MPI right here. Oh, shit, no, we can't do this. Yes, we can. We're not using memory for anything. Let's just push A. I'm feeling lazy. And then we can... No, let's do it the right way. STAR0. And then we go LDA I CMPI 0. We don't need to compare, we just need to load it. Because that'll set the 0 flag automatically. So we just jump if 0. Check char. Okay. Now, in here, if we get to this point, we want to do jump if not 0. No, jump if 0. Because if it's not, if I is non-zero, then we want to do LDA, or LDI 0. STAI. That'll reset I. I'm just using increment I here because it's a quick and easy way to write directly to I without having to do anything else. And we're just using I as a yes or no flag. Technically, I could just do spec I here to reset I, but I don't trust that. Programmer habits, I guess. You always assume that something might reach in and flip the bits in a weird way to go past the end, even though it's not supposed to do that somehow. At least I always do. The same reason why instead of just doing equals 0 as a loop exit check, I usually do greater than or equals to or less than or equals to 0 or less than or equals to whatever. Instead of checking if it exactly equals, I check if it's equals to or greater or whatever, depending which way I'm going. Screw it, I'm lazy. Let's just assume that nothing can go wrong. It'll save an instruction. Yay, speed! Not that it really matters. And then we want to set... Okay. I'm gonna be annoyed if it turns out to be... Okay, they don't allow you to do that. That's annoying. But not ultimately a problem. Yeah. We de-increment I. And the next thing we do is we LDA R0 to get our character back. Actually, wait, we need to do that. Shit. We can't just jump to continue here. We can't just jump to check char here either. Because if we do, we're going to clobber. Okay, here. Boom. We will do an LDR0. That may or may not be necessary there. Need to do the big site quests. You can start and earn them kudos. Get all them fossils. Get access to Fossil Island. Good stuff out there. Really good place for combat training too, in my experience. At least early levels combat training. Or lazy AFK for combat training. Thieving is such a pain to raise. There's much worse though. Okay. We load I into A. If it's 0, we jump to check char. If it's not 0, we make it 0. And then we load R0 back up again. And we... Did I never implement and or not, etc.? I don't think I ever did. Okay, we could do this with addition, but I'm not doing that. We're going to have proper... Yeah, I never did go in and implement... Group 6 or Group 7. They're encoded, but I never actually implemented them. Okay. Well, let's fix that, why don't we? First, let's compress this a little bit. Okay. Got a couple boops of unhappiness. Why is this... No, go back to being the right color. Okay, Group 6. My poor frame rate is suffering a little bit. Or a lot of it, as the case may be. Okay. Now, do I care about the overflow flag? For shifts and such like. I don't think so. No. Maybe? I certainly don't care about the carry flag. That can go away. I do care about the 0 flag. Now, we might as well set negative. I don't think I care about overflow. They don't really have a meaning for this. I guess if I change my mind, I can come back and fix it later. Okay. Now, and or not an XOR. And or not and XOR. Move all these one tile farther apart. There we go. Like that. And none of these matter what direction they come in. They just care they have 2 parameters. Except in the case of not, that only has 1 parameter. Oops. We better drag these downward so they're easier to line out. Which one's parameter 1? The bottom one, okay. I did wire these up correctly, right? I should go check. We'll assume they're correct. And if it doesn't work, then they don't work. Alright. That was easy and fast. We can condense this slightly because we don't have the carry line at the top taking up space. Boom. Okay. Now we need to add some instructions here. These are group 6 instructions. So there we go. And or not and XOR. Okay. I should also do ORI. Oh. Why am I loading R0 into LDA? I should load LDI mask and then OR R0 and then STA R0. And then jump to continue. Okay, let's just try this out. What's the worst that can happen? Should be 86, not 118. Because I did not remember to watch. Because I didn't actually do any of the stuff I was supposed to do. Okay. I need to set R0 to 1 at the beginning. Not R0. I need to set I to 1 at the very beginning. Because the first letter coming in is not a space. Okay, what the heck? Oh. No? That's right. What? Okay, let's run this again. Okay, we load 118. That's V. We store that to R0. We load I to A, that's 1. It's not 0. We jump to check character. No. It's not 0, so we don't jump to check character. Oops. We did increment I, so I is now 0 again, like it's supposed to be. We load the mask into I. We OR it with R0. Storing the result in A. Wait a second. No, we're doing this wrong. We need to unset. I need to unset this bit. I need to invert this and AND it. Yes. How do I make any money at this job anyway? Okay. Okay, we've copied a capital V in. Alright, it's working. It is not working. Why is it not working at that point? This is where I wish I could step backwards. Okay. Now we're at the A. And we do our ANDing. We write our A out. We load the R. We store it in R0. We load I. Why is I still set? Keep a close eye on when I gets set next. I is set to 2 here for some reason. What the hell? Oh, but let me guess. No, that doesn't make sense. Oh, yes, carry must be set. Okay. Increment needs to be add without carry. How could I miss something so obvious? Okay, where's the adding engine? Okay, currently we do not have an add without carry. So I will have to add one. But that shouldn't be too hard. Go ahead and make some space here. Like that. And then we have a 1-bit mux. Okay. Like that. And that should be a carryless add. See, this needs to be an off value. Okay. All right. We could shrink this even more if we had to not. There we go. Okay, we should have a carryless add now. Okay, there we go. Lovely. It's not often I have to worry about how ASCII characters are actually encoded. I'm almost surprised I actually remembered that little tidbit, that the difference between the capital and lowercase ASCII characters was 1 bit. But ASCII was specifically designed so that to do conversion between upper and lowercase, all you'd have to do is flip a bit in each character. Which explains its somewhat weird layout. Okay. Dancing machine. Okay. Pseudo-random number generators. This level you get one input. We call this initial seed. The seed is put through the following steps to produce a pseudo-random number. Oh, we're gonna need to implement shifts. 8-bit XOR shift RNG. Okay. Oh, we're gonna need modulus too, probably. Okay. I don't really want to implement division on this computer. But modulus is super useful to have available. And some kind, helpful soul did give us handy dividers. So we could actually go implement div. And the problem is the space where I was planning to implement mol, div, and mod, aka group 5, is now full with other more important instructions. Alright. I'm glad they don't expect you to run your make your own. Or decide your own pseudorandom number generator. We could calculate the modulus using software divide, but that would be a pain in the butt. I should probably just rig a hardware divide in somewhere and either throw in a temporary instruction or something, because I don't really want to have hardware divide permanently. I mean, it'd be useful. If I'm going to go through the work of rigging it up, I suppose I probably should implement it permanently. The trouble is that hardware multiply is a pain in the butt because it requires a 16-bit output, and I have no 16-bit registers. And I don't really feel like putting special logic in to write to a second register. I could replace the entire output line with a 16-bit output line. Replace the A register with a 16-bit register. And then just, for most purposes, only allow access to the bottom 8 bits. That would be dumb, though. It'd be the right way to do it in some ways, but it'd be dumb. But then I would need to have a separate instruction for grabbing the top bits and the bottom bits of the A register. Which would be... If I wanted to allow multiply, I'd want to design my computer from the ground up to really support multiply properly. Is there a really easy way to do 8-bit modulus? Let's see. Actually, I can probably do shifting to get modulo 4. Yeah. I can probably shift it. Because if I take Not sure why I didn't think of this instantly. Where'd that damn calculator go? It wandered off. What's that? There it is. Okay. Do I have this set to 8-bit? No. There we go, byte. Okay, now. Let's say we got... 145 as our random value. Hello? Is there any way to make this thing not signed? Of course not. That would be useful. Why in the hell would you implement a calculator that only can do signed arithmetic? That's stupid. Okay, well that's not useful then. Anyway, I'll just have to do it in my brain instead. Or brain. To get modulo 2, you could shift it right 7 times and then shift it left. Or no, shift it left 7 times, shift it right. And that would, or just mask off the top bits for that matter. Actually. If I just mask off the top bits, the top 6 bits, that should get me the value mod 4. We'll try it. Let's go ahead and implement this random number generator first. Okay, now we'll put in our little function protector. Okay. Now we will pass in seed in the A register. So we want to do seed. Here we'll STA R0. Okay, seed is in R0 for now. We're going to go ahead and save our registers. This way we can clobber whatever registers we want. It won't matter. Because the function will handle saving and restoring them. Okay, so we'll store the seed to R0. And then I did not implement the shift instructions. I'll just pretend I did and we'll come back and do them later. I'm going to move the... No, I'm not, because I have them encoded already, so I'm not going to move them. I will... Yeah, we'll implement them later. Shift right. Use constant parameters for these, I think. So you want to shift the seed right by 1. And then you want to XOR the seed with that value. Okay. Then we do XOR or 0. And then you want to STA R1. Go ahead and push R1 as well. And pop one R1 at the end to restore it. Okay. Now, for the second step, we want to take and we want to do temp1, which is known as R1 in our code right now. We want to shift it right by 1. So we'll do LDA. R1's already in memory, so we don't need to do that actually. We can do shift left by 1. And then we want to XOR that with R1. Okay. We want to store that in temp2. Which we use R2 for. Help if I actually typed out tar2. Okay. STA, R2. And then for the last step, we want to shift that right by 2. And XOR it with itself. And then that will be the next seed, which will return in the A register, which is where it already is, conveniently enough. And we just do pop R PC to return. Okay. That is a very straightforward function. Then we'll just do a little thing called mod4. This will take its argument in the A register. And we will just mask it. We need to destroy everything except, okay. Like that. Yeah, this should get us mod 2. So we just do, and, oops, I need a name for this. Oh, what should we call it? We're gonna need to load the mask into a register. Okay, so what we need to do push R1, pop R1, and then we do STA R1 and we do LDI Boom. We load the mask into A, and it with R1. And then restore the original R1. So you can kind of start to see what the stack is good for. It's really good for saving registers. So if you need to use a certain register, you save it at the top of the function and you restore it at the bottom of the function. And then for the users of the function, it doesn't look like that register is being used. Some functions save their registers, some do not. So sometimes you have to do your own register saving in assembly language libraries and stuff. And the reason for that is performance, because you don't always want to be pushing stuff to the stack when you don't need to. And some registers are defined in some programming environments. Some registers are defined as used for certain purposes. You always assume that they're going to get clobbered. All right, let's go ahead and define the instructions we need. So these are all group 7 instructions. So shift left. Shift right. Rotate left. Rotate right. Is that correct even? Shift left. Shift right. Yeah, okay. Then we need to implement the actual code for the robot up here. Okay. In this level, you get one input. That's the seed. So we'll go ahead and do LDA. IO. Okay. Next output, next seed, mod forward, move the robot. Okay, so we're going to want to do a loop. Just an infinite loop. And then we will do see, let me think about this for a second. Well, we want to call RNG. This will take our seed and it'll turn it into a new seed. And then we will take that and we will store it off to the side. And then we will call mod 4. We'll write that result out. We'll restore the A register. Using push and pop this way is wasteful, but screw it, who cares? 1 cycle. I'm gonna guess that all cycles are the same length. I don't know. Technically, they don't have to be. Memory access might be more expensive than otherwise, but I really should be reading and writing from a register here. But we're just going to push and pop it, because... Okay. And then we just call RNG again, and round. We go. But we need to actually go implement the shift instructions to make this work. So... the problem here is I no longer have the space to do this unless I move the whole computer up. So let's just do that. Here, why am I doing this? If I want to move the whole computer, I can just Control A it. It doesn't like being dragged. The frame rate cries out. But that's fine, I can suck it up. Alright. We can just go ahead and copy this block right here. What the heck? Did it not copy any of those 8s? That was weird. Okay. Not gets deleted in the middle there. Then we go ahead and move this one out 1 space. Okay, 8-bit. We want shift left. Shift right. Rotate left. And rotate right. Move all this over a little bit so it aligns. Why did I do that instead of moving this over first? Also, I'm not sure. That is definitely hooked up in the wrong order. Because value is almost certainly coming in an argument. 1. Wait, how am I implementing these in? Okay, that's wrong again. I better go check how these instructions are encoded. I just realized. Okay, we're shifting A, of course. Oops, that's not what I wanted. I wanted the I to say. Group 7. Okay, yes. Argument 2 is the amount to shift by. And it is not a fixed value. Okay. Do I want it to be? No. I don't think I do. Oops. That doesn't mean I'm going to have to change my code a little bit. Okay, so the value is coming out in argument 1, which is the bottom one. There we go. Now, I really should have my immediate mode and versions of these instructions, but I can't be bothered. For 2 1s and a 2, yeah, no thanks. So instead, we're going to just go ahead and push R3. And then we're going to go ahead after STAR0. We're going to go ahead and set this up. We're going to do LDAR0, LDI 1, STA R3. Okay. And to save ourselves a little tiny bit of space, we're just going to increment R3 so we get 2 instead of 1 for this one. All right. This should work. His problem. Short circuit. Where was the short circuit? Damn it. Ah, click past it again. Stop it, you idiot. Ah. Keep clicking past the damn. There we go. That switch. Oh. No, wait. Yeah, this one's correct. This one is not wired up correctly. Oops. How'd I do that? Very carefully, that's how I did it. Okay. Go back up to the main computer. Okay. I don't think it's doing what it's supposed to be doing. Okay, why is it complaining here? It hasn't even had a chance to do anything yet. Okay, this should call RNG. Push some values onto the stack. Why is the robot moving? What the hell's going on here? Okay. Let's set a breakpoint there. He's never hitting that. What is going on? Why is it going to there? That's weird. Oh. Of course. I forgot to set the bank registers for the stacks. So the R stack and the D stack are in the same place. Okay, where's the stack bank? SDMB and SRMB. Okay. If we set the bank registers. There we go. Finally. It helps if you have two stacks. You set them to different memory banks so they don't overwrite each other. Otherwise, you get things like return instructions taking you to weird places. And that's not good. Okay, robot racing. Okay. This time you're controlling Fastbot. He doesn't see what is in front of him, but he can turn to a new direction and move in the same tick. So you have go right, go down, go left, go up. Use the smallest program I can. Okay. It looks like this is a repeating pattern. So we want up, left, down. Right, right. Up, left. Okay, so we're going to want a little more complicated than that. Pretty sure this is a well-known-ish fractal. So we want to do a chunk of code. Oh, you know what? We're gonna smoke this. Because our instructions are half size. As long as we keep it to a relatively small number of instructions. I don't think the actual number of instructions are going to matter though, because they don't seem to have limits. Okay. Go. Got our movement constant set up. In proper up, down, left, right order. Now, we need to I wonder if there's a trick to this where we use an offset and move him through the course rotating everything. Let's see. Right, down, left, up. Yeah, we can, if you add one, or, you know, if you add not to the... If you rotate our numbers, we can rotate his view of the world. Okay. And I think what we want to do is we want to write a bit of code to move in that pattern. And then we want to write a little bit of connector code that just moves him around a corner and rotates the world. Except I don't think we actually want to... Like in this case, we don't want to rotate the world. Yeah, okay. Well, let's write a simple function to move through this pattern. We'll call it fork it because fun and shape of the sub pattern. And then we will do let me think. Trying to decide, do I have any easy way to go ahead and use fewer instructions to issue a static move command? And I don't think so. And actually, I don't think I want to use these constants either. I think what I want to do is assign these to registers. And then I can rotate those registers. If that makes sense. Let's do some setup code. Vector functions. And then we will do LDI. 0. STA. Right. Increment A. Nah. Let's do this in the correct order. Okay. Oops. It's gonna be interesting if this actually works. It should. But I'm kind of curious if it will. It does work. Okay. Cool. Alright. So we go ahead and load up our initial values. And then we're going to want to have a rotate instruction to rotate the world. I think. But we'll get there when we get there. So for now, we want to do LDA up STA IO LDA right STA IO LDA down STA IO LDA right STA IO STA IO so we go up right down right right up then we go left, up, right. Okay. And then up, left, left. Down, and left again. And then up. Okay, let's run this code. Oh, I need to actually do call fork it. Okay. Oh, we need to do a pop R PC at the end. That gets him to here. Now, actually, do I want to implement functions for each direction? I think I kind of do. Go ahead and label these as registers. And then we do up. Because we're not trying to get better speed, we're trying to get smaller code. Yeah. Okay. And then we replace all of these instructions with calls, which is already saving us code, I think. Certainly not saving us speed. We could probably do some transforms to cut this in half by flipping it. Yeah. We could flip this section. So up, right, down, right, right, up, left. Let's see. Up, right, down, right, right, up, left, and then boom. And then we would flip and go through that sequence in reverse. With the up and down directions inverted. And left and right inverted. No. Because there isn't really a divide between those two that we can do. This leaves us here. And then to get it, we need to have the up between the two. And then we do right, up, left, left, down, left, up. No? Okay. If we went through this in reverse with just right and left inverted, it'd be the same. How would I flip those and then flip them back at the end without being a problem? Would it be shorter? And how would I go through this in reverse? I don't think it's a reasonable thing to do. I'll mark the middle point anyway. If I didn't have to go through it in reverse, it would be totally reasonable. Yeah, we'll leave it alone for now. Okay. So we fork it. And that leaves us sitting on this tile right here. So we move up. And then we rotate. So we want to do LDA. Okay, let's start out. Up is going to become left. Let's load up R. Now we want to load. Yeah, we want to load up R. Damn it. And we'll store it in R4. Just to get out of the way. And then we do LDA. Basically increment all of them except up, which we set to 0. Okay, LDI 0, LDA, STA, up R, and then we just increment, down R, increment, left R, and increment, right R. They no longer mean what they used to mean. They're all rotated. Let's run this. Oh, I forgot to call fork it again. Oops. Damn it. Okay. I should move this bit into its own scrolling removes keyboard focus, which is a huge problem. Okay. That'll allow us to reset the transformation so we can redo it more easily. Nope. I screwed it up. Okay. So up has to become left, which is 2 actually. Wait, yeah. Oops. No. Yeah. Okay. Okay, you know what? Let's just do this the proper way. LDA, left R, or STA, up R. Should implement a rotate instruction. And then I could rotate it as many times as I needed. Clockwise. Okay, you know what? Let's do that. Let's have it rotate clockwise. Because that way, up becomes right. Right becomes down. Yeah, so we just need to add 1 to rotate clockwise. Okay. Okay. Now, I need to set my SDMB one, SRMB 2, set my stacks up basically. I can use stacks in here. I probably don't need to use the stacks at all, but I'm gonna do that anyway. Yeah, because I'm not using R4 anywhere else anyway. So we do LDA up STA R4 LDA right STA up LDA down STA right Damn it, I scrolled and it lost. LDA. Left. STA. Oops, that's not right. Okay, LDA up, store that in R4. LDA right, store that in up. LDA down, store that in right. Then we want to do LDA left, store that in down. And then LDA R4. And store that in left. So this should rotate counterclockwise. Yeah, counterclockwise. Which I said I was getting back clockwise and I did the exact opposite. Oh well. There's probably an easier way to do that, but we don't have that on it right now. Okay, let's try running this. Nope, not even close. What the hell am I doing? Okay. We are loading the up register and storing it in R4. We're loading the right register, storing it in the up register. We're loading the down register, storing in the right. Loading the left, storing in the down. Loading the old up register, storing in the left. That should mean that after we finish the counterclockwise rotation, we should be sitting right here. We want to order an up movement. So now we need to order right. Let's go ahead and run the bot out at that point, and we'll see if it actually does the right thing. Okay, so supposedly we're rotated now. We loaded 1 into the register. What are our orders again? 1 is go down. It's supposed to be 3 for go up. That's exactly what we ordered, though. We don't want to order right to go up. We want to order left to go up. Okay. Yeah, we say left. Okay. We're not rotating the right direction. This is actually rotating counterclockwise. What the hell am I thinking? No, it isn't. Let's just call it rotate. We'll call it 3 times. And then we should move right. Assuming we got this correct before we call it fork it. Okay. That is correct. And then he proceeds to move through the pattern. No, he doesn't. Why the heck not? What? Okay, because we end up here, which would be equivalent to him standing here before the rotate. No. It would be equivalent to him standing here before the rotate. So you have to rotate and flip. Okay, we can't just... And we don't want to actually... We don't actually want to rotate. We want to just do a transformation on it. How am I going to do this? Yeah, because it needs to be... Right and left need to be flipped. And we need to rotate it. Counterclockwise. I think what we just need to do is go ahead and take the code from reset. And hard code it for now. We can try to get fancy later. Scrolling removes. Okay. So we are sitting right here. And the old up or rather, here, let me get that level log back up. Okay. So moving up is moving right. No. Moving right is moving up. Okay. Moving up is moving left. Moving down wait. Moving up is moving right. and moving left by process of elimination. Okay, 3120 becomes 0213. Okay. Oh, whoops. I forgot to insert the last up move here. There we go. Okay, that was much more successful rather than trying to rotate it when we actually need to flip it. Boom. Okay. Now we just need to take those same directions and we need to flip left and right. Okay, let's just try that again. Nope, that is definitely wrong. Okay. Oh. Wait a second. We're not flipping left and right. We're flipping up and down. Or, up and down. Okay, now. Boom. No, that's not right. Stop. What the hell? Let's just go ahead and erase all this. I'll reset. We'll call right, get to where we need to be for the next start, and then we will do another transformation. Okay. Now, the next transformation, up, needs to be right. Down needs to be left. Okay. I thought I tried this. Right needs to be up. Wait, what? That's not right. No, I'm looking at this backwards again. We're over here. Sitting right here. So when we go up, we need to actually go left. And when we go right, we need to actually go up. Except... no. That's backwards. Yeah, that's backwards. That's what's screwing me up. Because if you rotate this into place here, it assumes we're in this spot right here. We're not. We're over here. So we need to go through that backwards. And to do this, we need to effectively flip some more things, I think. Is it as simple as flipping more dimensions? Okay, what happens if we flip both dimensions? Nothing works, that's what. Okay. Of course it doesn't. We actually need to change the operation order. In this case, we go up. We go right. We go down. Let's just go ahead and encode this part. We're standing right here. We go up. So to the right. We go to the right. Just up. Okay. Wait. Why am I being a dumbass? This is exactly the same. There's no transformation required for this. We just call right and run fork it a second time. Why am I being such a dumbass? I just assumed it has to be different. Okay. So now we transform. And I think in this case we just call reset. After we call reset. We call down. And then if we just reverse everything, we should be good. Okay, up is down, down is up, left is right, right is left. Oops. All right, let's see if this is right. This code's not going to win any awards for speed, that's for sure. Nope. Okay. We go through the first block perfectly fine. We set up our thing. We go through the second block. Oh, this is the problem right here. What is the actual direction for this? We need to go right, which is 0, which means we need to go up. Okay. Because I was assuming there would be a reset there, and then I removed that reset. Okay, we set up our transform. And then we move through. And here's where we find out if I'm correct. Yep. Okay. And then we need to check the second transform, which I did not logically run through. I just kind of did some assumptions. And it is not correct. Actually, wait. It is. Yeah, we just paused for a little bit while we ran through the second transform, and then off we go. Boom. Okay. It wasn't really a race, but I suppose there's probably a leaderboard somewhere that we can check. We only have 2 more puzzles left, and it's only 10:30. I say it's only 10:30. That worked out spectacularly well. We'll have 2 puzzles to do tomorrow, and then we can move on to phase 2. Phase 2, for the curious, I want to try implementing Forth on this machine. I've implemented Forth before using C, but I want to try implementing Forth on this machine. And that is why I designed this machine to have 2 stacks. Because having 2 stacks, hardware supported dual stacks, is going to make it way easier to implement Forth. And I even called them D stack and R stack. So if anyone wondered if there might be a reason for that, that is why. And I've been using the D stack and R stack just the same way that Forth would. The R stack is for return values and the D stack is for data values. Technically, a machine designed to run Forth would not need all these registers. Like the general purpose registers are basically meaningless on a Forth machine because you don't use registers for anything, you use stack. But a lot of instructions would be, a lot of words, they're called in Forth, would basically work a lot like the way the accumulator works. Pop 2 values off the stack, do something with them, push it onto the stack. A lot of things would be implemented as pop something into A, pop something into R1, add, push A. For example, would be how you'd implement add and Forth on this computer. I think that'd be interesting to do. Would use some of these sandbox IO things. There's somewhere around here, there's a thing that allows you to load stuff off of the disk. Not sure where it's at. File loader, here we go. Read bytes from your hard disk. We can output the contents of a file 8 bytes at a time. That's a rather large amount at a time. Basically, the idea would be to replace the program block, probably, or get rid of the program block, use a RAM block for program code, load the program in from external file, load, that'd actually probably be it. Just load the program in from external file. And then have the loaded program be a mix of assembly and Forth code. And then you could actually, what do I call it? Have an interactive terminal. I think you could do that. Yeah, we have a key press input thing. We could actually have an interactive Forth terminal implemented in this game. I think that'd be cool. And it'd be an interesting challenge. But anyway, for now though, it is 10:30. And although today's stream was a little short, largely because I took a nap at a bad time and did not wake up until late, I think we'll call it here anyway. And I'll see if I can drag myself to streaming a little earlier tomorrow. Or I shouldn't say drag myself. I can drag myself to bed so that I can start streaming a little earlier tomorrow. The nap today is certainly not going to help that, but anyway. Let's see, who's doing what tonight? It looks like Avi and Wasted are playing GTFO. Interesting. Let's rate Avi. GTFO is kind of an interesting game. I'm not sure if I'd like to play it, but it's certainly fun to watch. Also, if you ever hear jokes about Avi forgetting the baby, that is a reference to playing GTFO. Yeah. You have to ask him about it if you want to know. It's kind of funny. He may have forgot something at one point. But anyway, tomorrow we'll finish off those last two puzzles, and then time permitting, I will see about doing something interesting. Namely that Forth idea. And we'll see if we can get that done. Forth is pretty simple, but it's still, I'm willing to bet, a considerable step up in difficulty, even though I already have a copy of a self-implemented Forth that I fully understand laying around that I can more or less copy from. I will still have to translate it all into assembly and translate things like the input code and stuff like that into something a little more completely different architecture, completely different design. But anyway, until then, I hope you all enjoyed over at Avi's, and I will see you all later. Good night, and goodbye.